When I agreed to do this talk a couple of days ago, not talk, this intro, I was sure that I wanted to wear a green alien mask. It would be super. But then Valerie talked me out of it, and I also couldn't find one that fit. But like a lot of people who enjoy green alien masks in SETI, I have an interest in math and science and astronomy that dates back to before it was cool and extremely well paid. And here we are at Extension, which what we do is we provide an education to help people expand their horizons and also find new careers. So for those of you who are nerdy like me and want to put that math brain to a new career or to extend your career, we have classes in data science, in machine learning. We even have an awesome class coming up in quantum computing, I'm told. So if any of that floats your boat, please come and find me over there in the corner, wearing orange usually, or check out our website at extension.berkeley.edu. One more thing, in case the aliens come to us and strike the 5th floor of 160 Sphere, there are 2 emergency exits, 2 stairwells, one just outside stairwell A, outside roughly through these walls, and one on the other side, stairwell B, which is beyond the women's bathroom, so sort of diagonally across on the other side. And with that, welcome.
What's your name?
Oh, sorry. Ashish Mukherjee, and I'm a program director at UC Berkeley Extension.
Well, I did wear my human bodysuit over my alien infrastructure. This was the cheap model. They ran out of George Clooney ones, so I'm afraid they just have this little one left. But it's okay. It's getting a bit worn and tattered. But anyway, my name is Simon Steele. I'm the Director of Education and Outreach at the SETI Institute, and I'd like to welcome you on behalf of the Institute and on behalf of our CEO, Bill Diamond, who unfortunately can't be with us tonight. So. This is a monthly talk lecture series. Who has been to a SETI talk before? Okay, and I'm assuming by process of elimination, those who didn't raise their hands have not. Well, welcome. Usually these talks are down in Menlo Park at SRA International, and this is a first time we're up here in the city to maybe expand our horizons and hopefully yours. We are back in Menlo Park next month, and if you want to know more about that talk, just go to our website. For those of you who are new to the SETI Institute, in fact, a lot of what we do is going to be talked about here at this presentation. We have been around for 35 years, doing research not just in SETI, the search for extraterrestrial intelligence, but the search for life in all its forms in the universe. And I think that we will get the full spectrum of that exploration tonight at this talk. I was asked to give one little bit of advertising, and again, you can go onto the website for this. Bill wanted me to mention that the SETI Institute does have a scientific cruise coming up in Alaska. It sails at 7:30, so if you've got your bags packed, we're ready to roll. No, it's actually June 26th, July 3rd. One of our professors, Professor Lawrence Doyle, is going to be the host speaker on that cruise. And if you're interested in these sort of cruises of exploration, both of the wilderness and of the mind, again, please do go to our website and take a look at that. It should be a wonderful trip. I'm stowing away below decks on that one. So anyway, I'm going to stop talking. I am going to introduce Molly Bentley, who is the producer of the SETI Institute's radio show and podcast, Big Picture Science. So we recommend that you take a listen to that. They have weekly episodes, and again, you can go to our website or the Big Picture Science website to find out more about those episodes. And I'm going to hand over to Molly for tonight's talk, Are We Alone? The Search for Life in the Universe. Thank you.
Good evening. Well, I'm going to introduce each one of these scientists, and then they will give a brief discussion of their areas of research. Then we'll open it up for discussion up here, and then to questions for you. So think about the questions that you have for them. We'll begin with the woman sitting to my left here. Natalie Cabral is an astrobiologist, and she is the director of the Carl Sagan Center at the SETI Institute. She leads projects in planetary science and astrobiology, and she designs exploration strategies for Mars, Saturn's moon, Titan, and the icy moons of the outer solar system. She fully embodies her philosophy about the importance of exploration. And so her career has had highs and lows. She has trekked up the highest volcanoes, and she has dived to the lowest depths of lakes, because these places in the Andes are analogs for Mars. And what she wants to know is what the planet looked like billions of years ago and whether it was once habitable. Now, at the SETI Institute, Natalie is always friendly in the coffee room when we're refilling our coffee cups, but I always sense that she might prefer drinking her coffee brewed over a fire outside her tent in a remote Chilean desert. Am I reading you right?
Well.
Pretty closely, okay. Her achievements, I should say this, are not... Her achievements are not a SETI Institute secret. She has accepted an invitation to address the United Nations next week as part of the International Day of Women and Girls in Science. Please welcome Natalie Cabral.
All right, Molly, thank you very much for the kind introduction. And yeah, coffee is much better anywhere outside the Institute. What I'm doing at the Institute is, I'm just not the only one. I'm an astrobiologist, and there are probably 3 types of research about life in the universe at the Institute. One is hands-on, which is in our neighborhood in the solar system. Another one is...
do that radio thing.
Is,
Can you hear Natalie okay?
Is outside the solar system, and that's the exoplanet. Doug will talk about that, and then there is Seth. So what I do is try to understand, how to explore our solar system. What is life? How did it start? And what kind of instruments and technology we need to build to go and detect it. So to do that, what we do is try and find what we call terrestrial analogs to planetary environment. And this is what I do. I started my career analyzing Mars data from the Mars missions. I'm actually a member, or I was, because the mission just stopped, a member of the science team of the Mars exploration rover, Spirit and Opportunity. And so we first tried to understand if Mars was habitable. And this is what other missions are doing in other planetary bodies in the solar system, like Cassini did on Saturn. And once we found out that Mars was habitable, then the next question is that, did life actually appear on Mars? So we go back to those places on Earth that look like Mars 3.5 billion years ago and see what type of life actually is surviving out there, what kind of instrument does it take to detect it, and what kind of strategy do we need to deploy to actually find them out. So I spent quite a bit of time in deserts, but also at very high altitude, because in those places, like in the Andes, for instance, we have volcanoes, we have hot springs, we have lakes that are drying out because, unfortunately, like in the end, like anywhere else, the climate is changing. And so those lakes are evaporating, but this is a natural lab where we can go. And the reason I actually dive in those lakes is because it gives us an idea of what Mars could have looked like. It's an extremely, it's an incredible experience. But the point is that right there, the shock that we have is to realize that anywhere you look on Earth, we have yet to find a place where life is not. So those extreme environments are all inhabited. And in the survival strategies, the adaptation strategies are still the same. They have been the same since we have the record of life. And the cyanobacteria, this blue and green algae that we find in those places, are the same that were here on Earth 3.5 billion years ago. So this is our neighborhood, this is our garden, this is where we explore next. But we are also learning what kind of signature in different range, in different spectrum, this life is actually giving out. so that we can recognize them in other planets beyond our solar system. And I think this is a lot of what Doug is interested in.
Okay, terrific. Frank, can you do me a favor and just move the clock over here? Sorry, a little technical interruption. Doug Caldwell is an astronomer at the SETI Institute, and he is the chair of the Exoplanet group. Now, that's exoplanet, not X-planet, like Pluto. But is Pluto a planet again, Doug, for the record?
I don't think so.
You don't know, but we have to look
According
at the time.
IAU,
We don't know.
yeah.
Anything could happen.
I think it's a planet.
Okay, it is a planet. And you'll soon hear that when it comes for searching for alien life, exoplanet discoveries are some of the most exciting discoveries around. Doug has done, in addition to this, he's done what many explorers can only dream of. He has traveled 3,000 light years across the galaxy. That was the search space of the orbiting NASA Kepler Space Telescope, for which he was the co-investigator. And that provided us with the first extrasolar planet discovery. Tonight, you'll learn from him about the telescope's successor, TESS, the Transiting Exoplanet Survey Satellite, and another one after that, the James Webb Space Telescope. Please welcome Doug Caldwell.
Thank you. So I'll apologize in advance. I tried to fit all of exoplanet science on one slide and in 4 minutes. So, but I want to start with the top in the center there. We have this equation, weird-looking equation called the Drake equation, which maybe many of you have heard of. And it was put together by one of the founders of the SETI Institute, Frank Drake, as a way to sort of stimulate discussion about how likely it might be or how many alien civilizations might be out there that we could communicate with. And it's kind of a driving principle of a lot of the work at the SETI Institute to try and understand different terms of this. And it starts with N, the number of alien civilizations. R is the rate of star formation. And then the next three terms are terms that I'm going to talk about. They're kind of the easy ones to solve. The rate of star formation we know pretty well. There's about 5 stars per year formed in the Milky Way. The next one is the fraction of these stars that have planets, the number of those planets or the fraction of those planets that might be in a habitable area, somewhere that life could exist, and then the number of them that actually have life on them. And so in around 1995, we didn't know of any planets around other stars like the sun. Everyone expected there were a lot of them, but we didn't know. Fast forward to 2013 or 14, and we have today something like 4,000 known planets around stars other than the sun, and several thousand other candidates that have a good chance of being planets. So, and we now know also that there are more planets than stars in our Milky Way. On average, each star has more than one planet. And the plot of all those points is one way to look at those planets. And many of those, the yellow ones, each dot represents a planet that was discovered by Kepler. And the horizontal axis is the distance from its star. And so it's the orbital period in this one. So it's in days. The Earth would be at 365 days. And the vertical axis is the planet size. So you can see on the side there's an Earth, a Neptune, and a Jupiter. And what we found that there's a lot of small planets. There's a lot of planets at long orbital periods where they might not be too hot because of their star, too close to their star. But there's this region that's sort of highlighted where there aren't that many planets. And that's because they're hard to find there. And that's where we think the planets that might be likely to have life would be. They're not too hot, they could have water. And so we're trying to find more of them and trying to understand more about them when we find them. So the finding part's relatively easy. We did it with Kepler, which was a telescope that had about a 1 meter mirror, about this big. The understanding them is much harder. And there's two main ways that people are working to do this. One is we want to see if these planets have atmospheres so they could potentially have life. So one way is to look through this planet's atmosphere at the starlight coming through it. And the picture on the bottom there is actually a picture of Pluto, which may or may not be a planet, but it has an atmosphere. And that's a photograph from New Horizons looking back at Pluto as it was going away from the sun. And you can see the thin atmosphere, actually it's pretty thick around Pluto, that the sunlight is shining through. And by looking at that atmosphere, you can see what it's made up of, what kind of molecules and chemicals it has in it. We want to do that with planets around other stars. And it's much harder. It's a lot easier when you have a telescope right near the planet. So the other thing we can do is we can look at a planet directly, not the light going through its atmosphere, but the light that's coming from the planet or being reflected by the planet. That's also very hard because stars are very bright and planets are not very bright relatively. And because they're far away, it's very hard to see the planet's light next to the star's light. So in order to do this, we need big telescopes. Some of this work has been done with Hubble Space Telescope, which is a 2.4 meter mirror, so about 10 feet almost, not quite. But there's upcoming telescopes that are going to be launched in space. James Webb is scheduled for launch about a year from now in March of 2021, and it has 6.5 meter mirror, I think. So it's a big telescope. It's made up of separate segments, and it should be able to observe atmospheres of bigger, warmer planets. It still can't see atmospheres of planets like the size of the Earth. And in order to do that, we need even bigger telescopes. And so there are ideas people are putting forward to build really large telescopes. And one concept is this thing called LUVOIR, which stands for Large UV Optical IR Telescope. We're not very imaginative with names. But one of the ideas is it could be a 16-meter mirror, so like about 50 feet across in space. That's a huge undertaking that we don't really know how to do yet, but that's the kind of telescope that would hopefully be able to actually see atmospheres of planets like the Earth and measure, do they have water, do they have carbon dioxide, potentially other signs of life like Natalie was talking about. There are also telescopes that are being built on the ground. It's easier to build a really big telescope on the ground than it is in space, but you have this problem of the atmosphere. But people have come up with clever ways to get around that, and we've currently imaged a bunch of planets around other stars, nearby stars. They are big planets like the size of Jupiter, and so people are working on getting that down with some really extremely large telescopes called ELTs, imaginatively. And those would hopefully be able to see things like maybe the size of the Earth if it's a warm Earth or around a very nearby star. And so that's sort of where the science is heading. We know there are planets out there. We know there are a lot that are in regions around their stars that could be habitable. Now we want to see, are they habitable and do they have life?
Great, thanks, Doug. Seth Shostak, you in the room? There he is.
Well, only physically.
He's a radio astronomer at the SETI Institute, and he is the talented co-host of the radio show and podcast, Big Picture Science. Now, what I know about Seth from working with him on the radio show is that he's kind of shy. He prefers to remain on the sidelines, but you wouldn't think that he would be, because he has traveled the world to give thousands of public talks about SETI and science. He's written nearly as many popular articles on the subject. He is the recipient of the Carl Sagan Award for the Popularization of Science, and he hasn't yet met a reporter whom he's refused an interview, even if that reporter calls late in the afternoon of the radio show's weekly production deadline. But perhaps, with your encouragement, we can get him to open up to you tonight about the search not just for extraterrestrial life, but intelligent life, and that is the I in SETI. Welcome, Seth Shostak.
Thank you, Molly. Did I refuse to be interviewed by you? Is that what prompted this? I don't know. Anyhow, yeah, so when I joined the SETI Institute, which, as I like to say, was just before the Crimean War began, the only project there, the only research project there was SETI, looking for intelligent life. And it was a NASA project. Lamentably, 2 years after I joined, perhaps not due to me, but 2 years after I joined, that was killed by the US Congress. So ever since then, SETI has received no government funding, not in this country, not in any country. So it's privately funded, and that means that the effort is also somewhat constrained. But we're looking for intelligent life. Now, unlike these folks here, Natalie can find life on Mars by, for example, sending something to Mars and picking it up, or at least looking for it. Doug is looking for spectral signatures of maybe oxygen in an atmosphere of an exoplanet. Did you mention exoplanets? That sounds like a Monty Python skit, right? Yeah, okay, involving parrots, I think. So you could, one person watches Monty Python. In any case, that's relatively simple. If you're interested in, you'll pardon me, stupid life, that's easy to find. You can find it where I live, actually. So, but intelligent life is much harder to find because it's going to be farther away. It's less less commonplace. Okay, so we can't go there. There's no way we can go there. And despite the fact that 1/3 of the public believes otherwise, I don't think they're coming here. So how can you find it? You look for signals, and that's what SETI has done since 1960, when Frank Drake, the aforementioned Frank Drake, did the first SETI experiment. He pointed an antenna in West Virginia at a couple of nearby stars, hoping to tune in on signals that would be aimed our way. Okay, he didn't find anything. Well, he did hear something, but it wasn't the aliens, it was the military. Okay, so, but we have been following that paradigm ever since. Now, what's happened that's new, what's different? Why is it that I bet everybody a cup of Starbucks that we'll find ET within with the next 20 years? I have to keep recalibrating because time marches on, and my wife is buying Starbucks stock. I think that the point is that the equipment being used to do the search keeps getting faster. That's mostly Moore's law, right? It's just a computer technology. But beyond that, there are other new developments. The SETI Institute, as does the University of California, Berkeley, has a project to look for flashing laser lights in the sky that would tell you somebody's out there. And a scheme that I think has quite a number of very obvious advantages would be, forget the signals, because they might not be sending signals your way. I don't think any aliens know you're here because they're, in general, they're so far away, they haven't been able, there hasn't been enough time for radar, FM radio, television, all these things to get to them. So they don't know that Homo sapiens is here. You might tell your neighbor that next time they say they've been abducted. So they don't know that you're here, so they may not be sending anything our way. But the universe is 3 times as old as the Earth, so there may be very big things out there. And one way to find the aliens, at least the more advanced among them, would be to look for artifacts, look for things that they have constructed.
The end.
The end.
You're done. Okay, thank you very much.
Can I have some bumper music or something?
So the scientists here have outlined 3 different ways that the SETI Institute is looking for life. They're doing more than that, but what we had discussed here is going to Mars, either with our rovers or examining Mars. Perhaps one day we'll put boots on the ground in Mars. We're looking at exoplanets and the chemical signatures around in the atmosphere of these planets. And then, as Seth said, we're also looking for technosignatures. So I wonder if we can hear from you an overview of what specifically you're looking for. And what is the most hopeful discovery for what you all are looking for? Now, if I have this right, on Mars, some of these signatures would be chemical, some of them would be technological. On Mars, you're looking for perhaps chemical life, maybe geologic, if you're looking for a fossil. If we get really lucky, maybe it'll be biological. With what Doug is explaining, it looks like we're looking for chemical signatures, and then with what Seth was saying, that's a technological signature. Can you give us an overview, and what is the most hopeful scenario for each one of you?
I can take that
Can
to
you take
start
that
with,
one,
because
Natalie?
I want to start by provoking a little bit things here. So we are all of us, the 3 of us, we are, and the scientists in general in the world are looking for life now in the universe, wherever it is. But the thing is that we don't have a definition for life. We don't have a consensus definition for life. We don't know what life is. And therefore, we don't know exactly if we will be able to recognize it. So this is why we're starting with things like, well, you know, the chemistry might be just like us. They might be sending signal that we will be able to recognize, or we might find signatures that we might be able to recognize in the atmospheres. So in terms of being hopeful as far as Mars is concerned, and the solar system in general, maybe with the exception of Titan, the moon of Saturn, because the chemistry is very different, is that we will be able to recognize the signature of our own life, because the components of our own biology, they are very common in the solar system, in the universe in general. They are very common. And for Mars, as far as Mars is concerned, we have some common environment at the very beginning of the history of Mars. We also have some exchange of material between Mars and the Earth very early on, and it is very possible that some material from Mars came to the Earth. It's just a question of orbital mechanics. When you have big impacts at the beginning of the solar system, when planets are forming, material is ejected. If life ever appeared on Mars, we might have some of that material landing on Earth. And the joke around is that maybe we are the Martians we are seeking out there now. That would be, on early Mars, we can see for fossil,
We should clear up on the fossils. There are 4, I think, rovers that will be landing, or at least will be heading towards Mars this summer. And I think it's the first time that, let's see, what are all the countries? That Russia, the United
China.
States, Europe, and China will all be on the red planet at the same time. So when you talk about fossils, you mean literally fossils. You
I do.
dig down, not dug down, that's you,
Yeah.
but dig down, and we might see a fossil of a microbe?
Yes and no. When we are going, at least for the Mars 2020, which is the US rover, it's going to a place that's 3.5 billion years old. And that means that by that time on Earth, we already have fossils of what I call the cyanobacteria, the little blue and green algae, the stromatolites, those constructs. The thing is, though, that the history of the environment on Mars and climate is not the same as it was on Earth. And very, very early on, you have all sorts of things. The atmosphere has disappeared, and UV, the ultraviolet radiation, is coming to the ground, and this is UVC. This is something that is going to dissociate your DNA. This is going to destroy life. So whatever is out there on Mars, we might have some difficulties finding it at the surface, or maybe exposed, through erosion. That might be the other thing.
That's why we'll be digging. Let's hold that thought there, because that's a lot about Mars to process. So it is a very exciting time for Mars and for the planetary scientists that study Mars. Moving on to these signatures. So we're looking at a lot of things on Mars, and that may be in the news soon. For Doug and for Seth, just briefly, what are the signatures that you're looking for? What is the most hopeful thing? Doug, you talked about all the different kinds of signatures we might find in the atmosphere of these planets, these wild, some of them are extraordinary planets, where they rain, they have methane, and they're dark planets, or they're watery worlds. Try saying that. But what you're looking at is their atmosphere. So what's the signature you're looking for? What are you looking for?
So as Natalie said, to first order, we don't really know what we're looking for. So we're looking for things that we see on Earth that indicate life. So we're looking for water, carbon dioxide, methane. And if we see lots of these chemicals, especially if they're in disequilibrium, meaning they have to be resupplied in some way, or they would not be in the amounts we see, that tells us that something is creating these chemicals ongoing. And now that could be geology, and so there's a lot of people trying to study geology of different worlds and how that could lead to different compositions of atmospheres. There's a lot of biologists who are trying to understand what are the signatures of life that we could see around these planets. So right now we're really trying to just see, are there planets out there with water and carbon dioxide and the chemicals we have in our atmosphere?
Water, carbon dioxide are the
methane.
keys. Methane. Do you need to see them all, or if you see oxygen, do you think, okay, there's life on that planet?
There are ways to make oxygen from
Okay.
Volcanoes and geology. So it's.
So what's the list again? It's water,
I think all.
Methane,
Carbon
dioxide,
dioxide, maybe carbon monoxide.
maybe carbon monoxide,
is a good
ozone.
one.
So it's a cocktail. It's a cocktail you're looking for.
And one sort of shortcut that might be nice is, and people have thought about this, if we could find chlorofluorocarbons.
Easier
they're
to
not
say than
made
watery
naturally,
worlds.
and they destroy our ozone layer, but they're something that's a signature of life on Earth because we made them. And so if we could see some, it's almost like a technosignature.
Right. And you're hearing from the scientists
Pollution, yeah.
that we're looking for life, but we only have the example of life here. And one of the I don't know if it's a mantra, but one of the sayings among astrobiologists, we're looking for life as we don't know it. So you have to imagine we're looking for what we know, but also for what we don't know. So Seth, what is the signature? What's the most hopeful prediction in the work that you do?
Well, we have a somewhat simpler problem. You see, they can't even define life. This may surprise any of you who've been through the 10th grade, because there they told you, well, it reproduces and it uses energy and it moves around and all these things. These are all true, but you can find exceptions to all of that. So there really isn't any good definition of life. But there is a good definition of intelligence. If you can build a radio transmitter, we consider you intelligent. So, just fill out the forms that were left on your chairs, and we'll consider future invitations carefully. So we're looking, but in terms of what kind of signal we're looking for. As I say, signals are one thing that we do look for. Artifacts would be something else. You know, if you saw that somebody had rearranged the stars in their neighborhood into a line or a triangle or something like that, you would say, you know, that doesn't look normal. So that would be one indication that there's something out there clever enough to move stars around. But the thing we usually look for are what are called narrowband signals. The public thinks we're looking for, you know, the Fibonacci series or prime numbers or the value of pi or something like that. And we can't even do that, even if you thought it was a good idea, because of the nature of the technology that's used. So you can't do that. What you look for is a signal that's at one spot on the dial, just like, you know, when you came in here, maybe you were listening to KGO at 810 kilohertz on the dial, or KDFC at 103. I don't want to presume your taste in music or talk radio, but it's at one spot on the dial, more or less, you know, and that's the kind of a signal that a quasar, pulsar, they don't make signals like that. That's a transmitter. So if you're getting a signal like that from the sky, I mean, it could just be a satellite, but if it moves across the sky at the same rate that the Earth turns, in other words, the same rate that the stars move across the sky, then you can say, all right, let's call the papers.
Now, Seth, we've seen is everyone here, or has anyone here seen the movie Contact? Okay, like it's a good film. You remember how she had the headphones on, Jodie Foster? For those of you who have not seen the film, she wears headphones at some point. She's listening for a possible signal. Are you actually listening? Are you listening? Will you hear a sound, or is it something that registers on the computer?
Well, see, the thing is we monitor 72 million channels simultaneously with the Allen Telescope Array, which was presumably up here on the screen. That's the current receiver. So that would require 36 million pairs of earphones. We can't afford all the grad students to put on the earphones. We can't afford the popcorn to keep them happy, and it would mess up their coiffures. So we don't do that. It's all done by computers. There's no audio whatsoever. I mean, the TV people have occasionally asked, can we have some audio of what it sounds like to listen for ET? And the answer is no, because we don't have it.
I'm glad that you said that that's something the TV people ask, but radio would never ask that. A radio reporter would never ask such a simple question.
TV is an audio medium. I mean.
Now, I wonder, so all of these methods are working together. We were comparing and contrasting them. But what I'd like to hear is from one of you or from a couple of you, how the methods work with each other in tandem. So if one of you were to pick up an encouraging signal, does the other method step in? So does Doug look at the planets that where Seth, the method that Seth said, where if you find if we pick up a signature, do you look at the planets? How looking at Mars is maybe you check out the planet by going there, or would you turn a telescope to Mars? Could you give us an example of how they work together, how you work together to confirm some of these signals?
Well,
or follow up on them?
you know, there is something much more basic than that.
I know you want to talk to me.
No, I don't want to talk to you. But the thing is that the more stupid life you find, microbial life, simple life, the more we find, the more there is a chance that we will find intelligent life and in abundance. This is a statistical universe. So the more we have small things, the greater the chance is that you are going to have bigger and intelligent things. So this is one way, that thing works. The other one I already talked about, which is basically we learn in a solar system to recognize the different signatures of environment favorable to life, and trying to understand if there is something that's really unambiguously just life. So far, we don't have anything. The only thing is what Doug was saying, pollution, the thing that we are putting into the atmosphere that's not natural. Other than that, it's really hard.
I think one synergy we've had is the planets that Kepler and now TESS found that are potentially habitable, I think, go on to the observing list for Allen Telescope.
They do. But in the early days of planetary discovery, exoplanet discovery, we would look at every new exoplanet system, thinking, okay, that's a hot Jupiter. That may not be very interesting for ET. But on the other hand, if there's a big planet, there might be a small one. We used to do that. We don't do that anymore. And the reason we don't do that anymore is now we know that roughly 1 out of every 5 stars, this is a very preliminary estimate, but that's what's usually cited by people when they're citing anything. 1 in 5 stars has a planet that's more or less the same size as the Earth, presumably the same composition as the Earth, and at the right distance from its home star, so the temperatures are of the same salubrious quality as you enjoy here in the Bay Area. So those, because that's such a high percentage, right? If it's 1 in 5 stars, there are like 250 billion stars in the Milky Way. If it's 1 in 5, that means 50 billion cousins of Earth are out there in our galaxy. So, why be picky? We don't, we just look at all the nearby ones.
So, and something else too is that you're talking about habitable zone and you're talking about planet. But what the solar system exploration has been telling us is really that you can be outside of the habitable zone on the moon and still have habitable environments. And so we also know that there are way more moons in our solar system than there are planets, and much more habitable environment than there are planets in the habitable zone. And some of these moons might be just very interesting places for alien civilization as well, to be doing some work in their own system.
If anybody saw Avatar, remember Pandora? The inhabitants were modestly intelligent.
If we talk about getting up and personal with alien life, I think we have to be prepared for some disappointment. That sounds very exciting. But some of these places that we're discussing tonight can be visited and others cannot be visited. And there are trade-offs here. So if you go to Mars and we find evidence of life, maybe it'll be alive, but it's more likely that it'll be evidence of a past life. We're keeping ourselves hopeful about that. But one day we could probably put boots on the ground. But you probably can't have a philosophical conversation with a microbe. Maybe you can with an intelligent life, but it's unlikely that we can go visit that life. And then what Doug may find these worlds, they may find these worlds that scream habitability, that perhaps, I know Seth is looking at scream, no, not literally scream, but we may not be able to visit them either. So can you talk about some of those trade-offs?
So in one of the real kind of like golden signals that we might see in exoplanet science is we now know that the star nearest to our sun, which is only 4 light years away, it's actually a system of 3 stars, has planets in the habitable zone around one of the stars. And
what's the name of that star system?
That's Alpha Centauri, and the star Proxima Centauri, which is a little tiny cool star, is known to have planets in its habitable zone. And the other 2 stars in the system are much more like the sun. And they may or may not have planets. And because of their proximity to us relative to other stars, those are actually a place where we could image planets like the Earth, take a picture, study their atmosphere, with much smaller telescopes, like a meter or something. So people are thinking about doing that. The payoff would be huge. The problem is there's kind of only one star, maybe 2 or 3 other really close ones that we could do that to. So that's one opportunity where we could find something around a really close star. It still would take, many, many tens of thousands of years to get there with technology that we don't yet have. So
Yeah. Is that frustrating at all for you, knowing that you probably could never visit some of these incredible worlds?
No, not really.
Okay, good. Have an optimistic guy
Mars
here.
is good enough.
Okay, Mars is good enough. That's the slogan. All right. Seth, what are your thoughts on that?
Well, you mean in terms of actually meeting the aliens face to face?
Well, knowing that if you had a
Even
conversation,
assuming they have a face.
if you had a conversation with one, it would take a long time for the message to go
conversations are
back
probably
and forth.
not on. I mean, nobody knows how many, how many civilizations there are in our galaxy, right? Whether intelligent beings right now. Frank Drake has frequently quoted the number 10,000. That's his favorite number. But if you ask Frank, where'd you get this number, Frank? And he'd say, well, driving in on Highway 17 the other day, I just sort of figured it sounded like a good number. He admits readily that it's a guess, but Frank is a very smart guy, and his guesses are usually right about almost everything that I've been able to check. So if it's 10,000, that means the nearest aliens are on the order of, 100 to 1,000 light years away. That's the nearest. So let's say they're 500 light years away, and we pick up a signal tonight, right? Well, we're sitting here, so we missed the action, and we pick up a signal, and we found it. Now, to begin with, that there's a whole kind of a scheme for dealing with a suspected signal, but I won't go into that unless you really want to hear it. But if we got that signal, and you say, okay, we're going to talk back to them. Hi, we're the Earthlings, and we got a lot of used cars sitting around San Francisco we'd like to sell to you. That would take, in that case, 500 years, that signal to get to them, and then their response to that 500 years additionally. So that's 1,000 years turnaround, right? You wouldn't accept that with the people you text. That's a long time, right? So it's not going to be about conversation, but as I have said far too often, you know, I studied Latin in high school, and I read Julius Caesar. It was 2,000 years for that signal to get to me, but it was still interesting, modestly so.
Much better in Latin.
For the people in this audience, would you be excited if we did make contact with alien life, with an intelligent being? Sure. Yeah. What about with a microbe? What if we found microbe? Would that rock your world in the same way? So Natalie, that sounds like that may be the most, did you say it's more fascinating? It's fascinating. I thought she said it's even more fascinating. Okay, I wanted to hear the argument for that. We're going to take your questions in just a moment, but you know, Natalie, I was also being a little bit provocative with you by saying you can't have a philosophical conversation with the microbe. I have a feeling you would disagree with that because the microbes, even a fossil of a microbe could tell us something, and tell us what that is, and then we'll move on to questions soon.
Yeah, and you know, it's just like everything, everything alien, everything strange. It's just like somebody from another country. You find it weird as long as you cannot talk the language, cannot speak that language. If you start speaking the language of the microbe, which is basically chemistry, then they are going to start telling you a lot about the environment they are coming from, about how they were created, what's the environment they live in, and basically what they went through. This is why I'm going back to the Andes, because sometime in the middle of nowhere, in a salt lake, where it's really hot or really cold, all of a sudden you find a microbe that has a signature of an adaptation to very high radiation, or an adaptation to really cold environment when it's actually hot. It is telling you where its genome has been through over time. And so it might not be a discussion with Julius Caesar in Latin. This is really good, you should try. But it is still something that telling you something very profound about the environment that life took, the path that life took to get to that point, and what were the conditions of that life at the time it was formed. So the philosophy is for us, but you can have a conversation with a microbe.
I love that.
You should try, Seth. You should try.
If you find you're doing that too often, though, get help.
And Seth, I understand that there are some bottles of champagne in different, or there used to be, in different refrigerators around the world or around the country in case we did make contact with intelligent life. Would you pop that bottle of champagne if
You're
we...
assuming
if
that one of them is in my refrigerator.
Right,
I mean,
but if it's not intelligent life, but it was microbe, or just
Yeah,
the
it's-
evidence of a microbe, would you
Well,
pop
it's-
that
this
bottle
was
of
Jill
champagne?
Tarter's idea. Jill Tarter headed up this SETI research effort for decades, actually, and she was the prototype for the Ellie Arroway character in the movie Contact. But she made sure that there was always a bottle of champagne, indeed, at the observatories that we were using before we built our own. And there, I haven't seen a bottle of champagne. But in case we found them, you know, you'd break out the champagne. But I have to tell you that every time I would go to the observatory, it was a different bottle of champagne. It's true.
Okay, but would you pop it if we just found evidence of a
I'm not a
microbial?
big champagne lover, but...
Would you ask someone else to pop it? This is like pulling teeth,
No,
trying
but
to
I-
see if he'll pop this bottle of
But
champagne.
But Molly knows that we did in 1997. We picked up a signal that we thought was real. Nobody was thinking of the champagne. Nobody was thinking of the champagne. They were thinking, what do we do now? That's what they were thinking.
Do you have questions for the scientists up here? There's a microphone coming your way in the hand of Rebecca. Don't be shy. Put your hand up. Signal. You have to. This is all about signaling. You have to signal some way.
This is a question for Doug. Would space debris that is in orbit around the planet interfere with the telescopes that you guys are putting out there?
I'm going to ask you all to repeat the question because we want to get it on the record.
So the question is, would space debris interfere with the telescopes that we're building to do these searches? And yes, it certainly can. You might have heard recently there's been some launches by SpaceX to launch a bunch of communication satellites, and a lot of astronomers are up in arms because they're very bright, relatively speaking, so a lot of the ground-based telescopes have to deal with them. As far as debris in orbit, a lot of these telescopes will be far enough away from the Earth that that won't be a problem. They're going to be at a Lagrange point, so out past the moon to get away from the Earth for just such reasons, to get away from the dust and the stuff that's around the Earth and the bright light from the Earth and moon.
And the Lagrange point is the point approximately midway between the Earth and the moon?
There's a bunch of Lagrange points, but the one that they're going to be at is a place based on the gravity of the Earth and the Sun. There are two places around the Earth, one closer to the Sun and one further from the Sun, where you can put something in orbit and it doesn't take very much energy to keep it there. So it doesn't drift away from the Earth. It stays in the same place, so you can keep talking to it easily.
Okay, great. Other questions?
As machine learning and artificial intelligence continues to grow, will this help in your search for intelligent life or any life?
Good question.
Certainly, in the case of the search for intelligent life,
Sorry,
it's already
excuse me,
being
Seth.
applied.
Do you mind repeating the question?
Oh, I'm sorry. The question was, what's the role of artificial intelligence in searching for life? And the answer is that, you know, when you have 72 million channels for your receiver, I mean, you get stuff all over the place. And the question is, can you, in fact, you know, do a better job of sorting the wheat from the chaff? Now, there's a gentleman in the audience who helped us to try and develop a system where citizen scientists would do that. But, you know, citizen scientists, unfortunately, you know, take coffee breaks, they're unreliable, whatever. Whereas AI is thoroughly unreliable. No, AI is good, particularly machine learning. So that's already being applied, particularly at Berkeley, and we will be applying it to our own SETI searches as well.
But there's a part B to that, or part two, depending on how you number or letter things, which is, isn't it possible that the intelligence that we find somewhere else could be machine intelligence, that's the ultimate trajectory for any evolution?
I certainly think so. So our machines will talk to their machines.
If I may chime
Yes,
in?
please.
Yes, there is the other part to that is from what we learn in the solar system, we know the type of environments that our planets had very far in the past. And we also have the data now from Exoplanet. And what we're doing is using all of this to model potential, what we call coevolution, the coevolution of life and environments. We know that we are the product of 4 billion years of evolution on our own planet. Environment and life coevolve. The planet is giving you the physical and chemical environment for life to appear, but also constraints for the type of life that you will have. As soon as life is there, it's going to change all of its environment. The atmosphere you breathe today is not a result of the environment alone. It's the result of some little algae, the same one I was talking about, shooting oxygen in the atmosphere and changing it. So you have this coevolution going on. And we know that life that is going to appear on other planetary environment is going also to be co-evolving with that environment. So learning more about exoplanet environment and mixing it with what we know of our own solar system, with the help of AI, we are now starting to project what type of coevolution could happen on exoplanet or anywhere in the universe.
But we can't assume that that evolution would unfold in the same way, because isn't it true that there's just been a number of happy accidents, we might call them, that allowed us to be here today in this room talking to each other?
Absolutely right. This is why, you know, thinking that we are going, there is going to be some convergence, because nature finds the same solution to the same problem. And we can see also on Earth a number of times of when the same invention has been made by nature, like your eyes, it's been invented independently about 20 times on our planet. So there are some solutions for the same questions. On the other hand, you would take exactly the same planet, two Earth at the same time, same environment, exactly the same twins, but you tweak an event, an extinction or an asteroid, and today, what we are, who we are, first we wouldn't be here, and we probably would look very, very differently. We still don't know. We are talking about accident like asteroid or cosmic events, etc. But we know also that biology is mutating for reasons we don't understand very well. And this happened a little less than 1 billion years ago, and the result is us. Otherwise, we would be, happily having these discussions as algae in the pond right now. and we don't know why complex life all of a sudden just popped out of nowhere, but it's probably related to a mutation in the biology. So there are a number of things. You can have exactly the same environment, you tweak something at some point, and it will change completely the outcome.
So there are lots of different variables, it sounds like. If there are other questions while you're thinking of that, Seth, can you just remind us why the asteroid was so important in the rise of human beings, the asteroid that wiped out the dinosaurs? This is an example of this kind of happy accident, although it wasn't happy for the dinosaurs.
I thought it was to sell your company that's doing asteroid mining. It gets stuck. Well, yes. I mean, as some of you may remember, 66 million years ago, a rock slammed into the Yucatan and, it did away with the dinos, most of them anyhow, and led to the opportunities for the mammals. There were mammals beforehand, but, nothing was bigger than 20 pounds, right? And then suddenly there were big mammals, and eventually you. So yes, having more rocks, I mean, it's been said that, well, having too many asteroids might be a bad thing. It would wipe out societies. There was a book published in 2000 called Rare Earth, in which it was said, we are lucky not to have too many asteroids. But I would posit that maybe that's wrong. Maybe what we needed were more asteroids to get rid of the dinos a little earlier, because we wasted 150 million, I mean, they wouldn't consider it that way, but we wasted 150 million years on the dinosaurs, and we'd probably have the cure for death now if the dinosaurs hadn't been wiped out. So I think rocks are probably a good thing, shake things up.
Okay. Okay, another question.
So my question is about exoplanets. So you said there have been a few thousand discovered so far. So what do you think you could learn kind of cross-sectionally if there were two or three orders of magnitude more exoplanets that have been observed? So if you had, millions or tens of millions, but you have the same observations that we have today, no new technology, what could you learn?
It's a numbers game. Do you mind just repeating that?
The question was, what could we learn? I think my mic's off. What could we learn from more discoveries of exoplanets? If they were in the same parameter space we found them, we've really got a pretty good sample, as you can see by that plot I had that had lots of points filling it in. But we might, I guess we've been cut off. That's it. We're done. Show's over.
No, it's working now.
We might. Now mine's on. No, it's not. What we would hope to do is to push the boundaries of where we can find exoplanets, smaller planets around different kinds of stars at longer periods. And what I think the main thing that's going to tell us, and when we start to be able to understand them and if they have atmospheres, is what are the range of these conditions that Natalie was talking about. Do we see planets that are all carbon monoxide atmospheres, or all methane, or some other, ammonia or something, and just these different ranges of conditions that will allow us to understand the possibilities of environments that are out there, not just what we see on Earth or Venus or Mars. So I think that the diversity is what would help.
Just a pause in the questions. This brings me to a quotation about exoplanets that I want to run by Doug. He made it sound like, oh no. But I read that exoplanets are a window into the future and into the past of Earth, and that quote, they allow us to simultaneously see Earth from cradle to grave. What can other planets tell us about our own planet? Especially planets that are so strange and far away.
That's true. The thing that we know about the Earth around the sun at 4.5 billion years old, but we don't know what the Earth was like necessarily at 1 billion years old. But we do have exoplanets that are around young stars and much older stars. So if we can find more of those and understand, we see, oh wait, all the small planets around young stars look like this, or and so that does teach us about the evolution of planets around stars. And one question we still have is, how soon do planets form, and what happens in the early years? Do big planets like Jupiter come crashing in and scatter all the little planets out? We know that happens in some cases. So understanding the evolution of planetary systems, we can do that by looking at this snapshot of the sky around us.
Does that include our own fate? The fate of Earth? The ultimate fate of Earth?
I think we have a pretty good idea of the ultimate fate of Earth. The sun's going to expand and burn up the Earth, and in 4 billion years or something like that. So we don't know what's going to happen until that. There's a lot of debate about, how long are we going to still be habitable as the sun's warming up? Some people think we're right at the edge of it, in another 20 years. Well, I mean, from our own making probably, but as the sun warms, we could be, the Earth is going to become less and less habitable. Now, these are timescales of like billions of years, but we would be able to better understand this by seeing a lot of other instances of Earths.
But still, it's good to double check your to-do list. Oh, yes, yeah,
I
please.
just
Yeah, go
wanted
ahead.
to add
Natalie.
something to what Doug was saying, is that we can calibrate this with the history, the geological history of the Earth, because we've been through so many changes. The Earth today doesn't look anything like what it looked 4 billion years ago or 2 billion years ago. And right now, what astrobiologists are doing is to use the different epochs of Earth, when you had the snowball Earth, or you had a time when we had a CO2 atmosphere or methane atmosphere. We went through all these times, and we can find a record of this in the geological, in the sediment of Earth. So I think that this can be calibrated as well with the findings that we have on our Earth and on Mars and other bodies of the solar system.
Great.
Hi. So I know there's been a lot of excitement around kind of the idea of like something like Dyson megastructures or something like that. Do you think, do you think A, do they exist or would they be possible? B, would we with our current technology be able to detect them? And C, would they be like easier or harder than necessarily like radio signals or other things like that?
Okay, Dyson megastructures. Do you want to repeat that question and also give a quick definition, Seth, of what a Dyson megastructure is?
Well, the Dyson Sphere, how many people know what a Dyson Sphere is? How many people have lived on a Dyson Sphere? A Dyson Sphere, this was just an idea from the British physicist Freeman Dyson about 30 years ago, and a very clever one. He said, look, if you really want to solve the energy crisis, right, you can argue about coal or natural gas and all that stuff, but really what you want to do is take apart Neptune that nobody is using right now, take it apart, rebuild it as a big shell outside the orbit of Earth, line the interior with solar cells, so you collect all 4 times 10 to the 26 watts from the sun, or at least some fraction of it, and then beam them down on a microwave to the Earth. Now, you have to be careful so you don't cook a lot of birds and all that sort of stuff. But this is not impossible. This does not violate physics. The capital cost is high, right? But then again, you're not burning anything on the Earth anymore, right? It's totally clean energy. So he was suggesting that really advanced societies will have done this. And you might be able to find that Dyson Sphere because the outside of it will be a little bit warm. You'll get infrared radiation. People have looked. But what was the question
Well,
again?
there's part B and C. Yes, yes. So thank you for that quick explanation of what a Dyson Sphere is.
That isn't what he
Part B is,
asked,
do
though.
we have the technology, or
Yeah.
part B or C is, do we have the technology, right, to discover it? And what was the other part?
The whole thing was
Yeah, okay.
motivated by the discovery about 3 years ago, what's called Tabby's star. And I think that's what you're referring to, right? Yeah. Tabitha Bujayan, I mangled her name again. But anyhow, she noticed that one of the stars in the Kepler sample actually dimmed by 22% at one point. That's a lot. The sun never dims by 22%. You can go out every day and look at the sun. Don't recommend it, but you could do it, and you would notice that it gets brighter and darker, sunspots and all that, by about 0.01%, right? So 1 part in 10,000. But this was 22%, 1 part in 5. So what was doing it, and one suggestion that was made by a gentleman at Penn State was that they're in the process of building a Dyson Sphere. They don't have it quite complete. And, the part of it had gotten in front of the star. I mean, this is not unreasonable. It's not unreasonable. But it turned out that if you look carefully, when it dimmed, the star got redder. And that's dust. That's not Klingons.
Does that answer your question sufficiently? Yes. Okay, good. Take another question in just a moment, but I know Natalie wants to take a moment tonight to describe a new multidisciplinary roadmap. Are you prepared for that?
Why not?
Okay.
But we'll take another question.
Okay, that was the moment. We'll come back to it. The moment will be regained. Yes, sir.
My question is around each one of yours resolution to the Fermi paradox and whether or not you think life is exceedingly rare, very common, or very common and it can only get to a point, and based off of everything you know, how you think about that with your intuition plus everything you've observed.
It's a good question. Does everyone know what the Fermi paradox is? Well, I do this, how about hands up if you know, that's a good signaling. Okay. Doug, you want to give a quick?
Oh, I knew you were going to start.
I am going to start with you.
I don't know what the frame.
Quick overview. Somebody give a quick overview and then answer this gentleman's
Seth, give an
question.
overview.
Oh, the Fermi paradox. It was just an observation by Enrico Fermi in 1950. It's a bit apocryphal, but he probably did it, in which he'd just look around at lunch and said, well, so where is everybody? And he wasn't referring to the lack of company at lunch. What he was referring to the fact is that you can cross the galaxy. You could settle the entire galaxy in 30 or 40 million years, almost irrespective of how fast your rockets are. Right? 30 or 40 million years sounds like a long time if you're waiting for the Muni. But 30 or 40 million years is actually very, very quick compared to the lifetime of the universe, which is 14 billion years. So that means it's sort of like when the Spaniards discover America in 1492, whatever, within one generation, within 30 years, there were Spaniards all up and down the coasts of the Americas. So he was making that analogy. He was saying, if anybody wanted to colonize the galaxy in the last 14 billion years, they've had more than enough time to do it, so where are they? So that's the Fermi paradox. They should be everywhere, and we don't see them. That's the
I think the second part of your
paradox.
question is, what is your relationship to, can you answer that question?
yeah.
Is that what you were asking them? Yeah, so what's your response to that? Where are they?
Well, 1/3 of the public thinks they're here, but I don't, but a lot of people do. Well, there's an entire book written by a guy by the name of Webb, in which he essentially lists all the possible explanations for this. One that I particularly like is the fact that the galaxy might be urbanized, right? So if we blindfold one of you and spin you around, put you in a plane, and then take you 20 miles south of Winnemucca, Nevada, and then take off the blindfold, you won't know where you are. And you look around and you won't see anything except, sagebrush or whatever. And you say, well, I don't know where I am, but there's obviously no intelligent life here. This is not a slur on the great state of Nevada, but that, that's it. So it may be that we're in a part of the galaxy which is not terribly inhabited. I don't know whether I believe that or not, but I think that the real thing about the Fermi paradox is to remind yourself that it's a big conclusion, namely that nobody's out there, based on a very local observation. And as I've told Molly many times, I look out the back window of my house down in Mountain View and I don't see any bears. And yet there's been plenty of time for bears to get to my house. So maybe there are no bears in North America. That would be the wrong conclusion from a local observation.
I have to say, I've actually never heard you say that.
Well, I did, but you're busy reading something.
There is
Okay.
something else too,
Yes,
is that when you think about this, think about where we were 100 years ago. Our technology. So 100 years ago, we were barely starting to fly planes. And today we have telescopes and we have all of this technology and we are listening to signal. Even if there was a civilization not too far away from us, they would have to be looking in the same direction as we are at the same time, but also if we are only 100 years apart, we might just know that we are here because we cannot yet communicate with each other. That doesn't mean that there is nobody around. Just need that, we are just maybe not facing each other, or maybe we are not at the same time, in the same time frame, and it might not be that far apart. But there are so many parameters getting into play.
I guess quickly, sort of my philosophy on that would be, when we go look for things, we really usually don't know what we're going to find. And if we were to decide, oh, well, they must have been here, that means they're not there, and not bother to look, then we don't really know what we're missing. So in some part, I think we don't see them yet, but why not keep looking? And we'll learn a lot. And we've learned a lot of non-alien intelligence by looking and seeing, oh, there's planets everywhere, and there's different kinds of planets. And so I think keeping looking, we're going to learn a lot about our place in the universe, with or without them.
You are so true, because I think that one of the greatest things about science is not that science necessarily answers all the questions, but it learns how to ask better questions. And this is what we do by learning more. And if we are staying in place, then we'll never know.
I think we have time for one or two other questions. Do you have any other questions? This gentleman here.
I'm curious about
stories besides Tabby Star?
So the question is
Are-
about
yeah,
false
are
positives.
you asking about intelligent aliens? Yeah, because there have been false positives also for microbes, actually, on Mars. It was a big science news story in 1996, if you remember that. But no, well, we have had. I mean, we get signals all the time. But the equipment, and in particular the software, has gotten better and better at recognizing what's for real and what's not. You get signals, with our system, about every 10 seconds you get another signal. So this is very commonplace. But in 1997, I'll tell you this story. It only runs for about 30 minutes. I was at home, and the phone rings. I was having dinner, and it was the CEO of the SETI Institute, a guy by the name of Tom Pearson at the time. And he said, Seth, I think you ought to get down to the Institute. And when your boss calls you at home at dinner and tells you to get down to the office, I figure it's not good news, right? But I went down there, and everybody was lined up in front of the computer terminals looking at a signal. And this signal they had been following for a while, and it looked like the real deal. It really did. You know, because we would do simple tests, like move the antennas, this particular antenna was in West Virginia, but anyhow, we'd move it a little bit away from the star system we were looking at, and the signal went away. And then we moved it back, and it came back, and we moved it away, and went away, and came back, it went away, it came back, and went away. So, you know, I began looking around for the red phone to see if it was going to ring. We don't have a red phone. I kept waiting for the men in black. You know, they didn't come. I waited for, you know, I waited for the mayor of Mountain View to call, whom I know. He didn't call. I waited for my mom to call. She didn't call. Nobody called. Nobody was interested. It was incredible. There was no secrecy. People were, you know, sending out emails. Hey, don't tell anybody, but we got this signal. Finally, you know, this particular star system set, so we had to wait another 12 hours before we could pick it up again. And so I went up to my desk, and I was wiped out, of course, but I was sort of sleeping on my desk, and my phone finally did ring, and it was Bill Broad, one of the science reporters of the New York Times. And he said, well, what about that signal you're following? So they already knew about it in New York. So I think while there are protocols for what to do in case you find a signal, the truth of the matter is it will be in the papers right away. And of course, the papers that will run it first are the less reliable papers. So I believe you will read about this in the checkout line at the supermarket before you hear anything else.
But the idea there, that phrase, no secrecy, is important. So the idea that there could be a detection and then that evidence would be covered up and squirreled away somewhere and we would not hear about it, you're saying that's just not possible.
Yeah, Americans love that idea. They love conspiracies, but it isn't possible. And in particular, the first thing you'd want to do, and Jill Tarter was about to do this, call up somebody in another observatory and say, hey, would you look in this direction at this range of frequencies and see if you find a signal? Because you wouldn't believe it yourself. It might be a Stanford undergraduate prank. I know you're all Stanford fans, but, you know, you'd have to rule that out. So there's absolutely no way it could be kept secret.
What was it? Did you pick it up again?
We did pick it up again, yeah. It was a type 2 civilization. They weren't very interested.
Okay, we have one more question.
It was a Soho satellite.
Oh, do you want to?
Just very quickly.
Yes, yes, please.
Just to address your question as well. We have something going on in the solar system right now. And that thing is the methane on Mars. We have no clue. We have no clue
The
because
methane, yeah.
Methane can be geology, it can be biology, and on Earth is usually associated with both. So we cannot talk about false positive, we cannot talk about false negative, but something's going on out there.
Well, as we said, there are big missions coming up, 4 of them, NASA, China, Russia, and Europe, all going to Mars, so we want to follow those closely. Yes, sir?
I'm curious about the possible upside of the catastrophes that we're looking at here on Earth. Is it possible that we may make a signature that other civilizations could recognize as typical of our stage by destroying the climate here or through nuclear annihilation?
Why do you think they are not showing up?
They become very distinct, and could you look for such things elsewhere in the universe as signatures of nearly intelligent civilizations?
So not necessarily just the signature of a thriving civilization, but maybe one that was once thriving in the
That's the
throes of
L
some
in the
kind
Drake
of
equation.
catastrophe,
That's-
sort of it's kind of that bottleneck. And how does that civilization get through that bottleneck and survive? So the interesting question, could you find the signal of a civilization that was struggling?
I'm glad that the gentleman sees the upside in climate change.
That's the
No,
darn
probably
intelligent
not.
life.
Probably not, Gordy, because you would need a baseline. If you've been measuring, for example, the infrared emission from the Earth over the course of time, and you could do that relatively accurately, maybe you would notice that it went up. I mean, there was some discussion here about the chlorofluorocarbons in the atmosphere. Well, maybe you could find those. Well, to begin with, it's not easy to find them. That's point one. But point two is they went away 20 years later, right? So you need something that lasts for a long time. And I take it from your question that you're sanguine that the climate change problem will continue to get worse for at least 10,000 years. So in that case, maybe you could notice.
Right, I think we'll wrap it up there. So the summary right now, as they say in, maybe, I don't know if they say it in radio astronomy, but they say it in radio, stay tuned for this news.
And come visit us.
And come visit us, which is something the SETI Institute also says. The aliens, thank you for coming out.